welcome to this lecture on the course of computer aided power system analysis. In the last lecture, we have discussed about the concept of contingency analysis, and in that lecture we have argued that for the purpose of contingency analysis, it is not required to have a very accurate value. Rather, we are only interested that whether the system would be operating in a secure zone or not in the case of any contingency, that is the outage of either a generator or a transmission line. So, then we said that because of this fact that we really do not have to compute the full AC power flow analysis to analyze the effect of any single contingency, but rather we can possibly take some simplifying assumptions and do some kind of rough calculation to arrive to our conclusion whether the system would be operating in a secure zone or not after a contingency has occurred. So, then essentially what we have done is, so we are talking about contingency analysis. Now, today we will be looking into the basic concept that how do we go about it. So, contingency analysis. So, we said that we really do not have to do any kind of a complete AC load flow analysis, but we have to do some sort of approximate calculation. So, these approximate calculations we carry out by using something called sensitivity factors. So, we use something called sensitivity factors. Now, what are these sensitivity factors? These sensitivity factors, now there are actually two kind of sensitivity factor, which is called generator outage sensitivity factor. This is GOSF, generator outage sensitivity factor, and the second one is line outage sensitivity factor. So, we have got two types of sensitivity factor, or rather we use two types of sensitivity factor, which is called generator outage sensitivity factor and another is called line outage sensitivity factor. Now, what do they mean? Actually, what do they mean? So, GOSF is defined as, now what is GOSF? GOSF is basically defined as, first let me write down the expression and then we will define what are this quantity. It is defined as del Pi by del Pk. Right now, it is looking very cryptic, but let us explain. Pij is the real power flow over a line between bus I and bus j. So, this is Pij, and what is del Pij? And del Pij is of course then change in Pij. Similarly, Pk is the injected power at bus k, and of course, del Pk is change in Pk. So, then therefore, what we are essentially saying? We are essentially saying that GOSF is denotes that how much, by how much, or rather basically GOSF is nothing but the ratio of change in power flow over a line between bus I and j due to the change in real power injection at bus k. So, this is basically the definition of GOSF, generator outage sensitivity factor. So, what it is exactly means? So, let us again take some very simplifying example. Let us take some very simple example. So, so, so so this is bus 1, bus 2, this thick lines are buses, nothing but that is the junction points, bus 3, bus 4, and let us say there is also another line between them. How does it matter? And let us say there is one generator connected at bus 1 and let us say another generator is connected in bus 3, and there are loads, etc. So, now for example, if I take a line between let us say bus let us say 1 and 3, or let us say bus 1 and 4. So, then therefore, GOSF would be, and let us say we are talking about the change in real power injection at bus 3. So, that means GOSF for this case would be delta P14 by delta P3. Delta P14 is nothing but how much by how much the amount of real power flow has changed over this line between bus 1 and bus 4 due to some change in injected real power at bus 3. Now, the question is from which this change would be measured. Basically, I mean whenever you are talking about any change, so then obviously that change would have to be measured from some reference value. This reference value is the essential, I mean this particular reference value is essentially nothing but the pre-contingency steady state stage. So, then therefore, these changes are measured from the pre-contingency steady state case. So, now what we are actually saying? Now, let us go into a little deeper. Suppose I know this value of GOSF by some means. Suppose that GOSF is known. So, if GOSF is known, by some value, I mean whatever, I mean by some means, I mean we will see that how this particular GOSF is to be calculated. So, if GOSF is known, so then therefore, if I know that what is the change in P3, then we can immediately calculate that what would be the change in P14. Similarly, we will also have to define GOSF for each and every combination. For example, for our case, we can simply say that it is, let us say this is GOSF, let us say Ij due to k. So, we can say that this GOSF is basically Ij due to k. So, then therefore, when I say that GOSF with a subscript Ij and with a superscript k, right, it only says that this is del Pij by del Pk. So, then therefore, for each combination of this generator and the line, we will have different values of GOSF, right. And if these GOSFs are known, so then therefore, if there is a change in the real power injection here, so then therefore, immediately we can calculate what would be the new amount of, or rather what would be the change in the real power flow over a line between bus I and bus j due to some change in uh, injected power at bus k. Now, suppose, just take an example. Now, suppose that this particular generator has been generating 100 megawatt, and let us say this particular generator has been generating 50 megawatt, suppose, in the steady state. So, then therefore, now if this particular generator goes out, if this particular generator goes out, so then therefore, what will happen? This particular so then therefore, this particular generator would not give any amount of power. So, then therefore, delta P k, in fact, any delta P k is actually given by P new minus P old. When we say that P old, this is nothing but this initial steady state value. So, then therefore, if this particular generator goes out, so then in this case, what would be the value of delta P k? It would be 0, because when it is going out, it is not giving any value of power, and earlier it was 50. So, then this delta P k would be minus 50 megawatt, right. And if our base is, let us say, 100 MVA, so then therefore, in per unit delta P k would be is equal to minus 0.5 per unit for base is equal to 100 MVA, correct. Now, suppose we know if all GOSF I j k are known, we will see that how these GOSF k are known, I mean, or rather how to actually calculate this particular sensitive factors. So, then therefore, if all these GOSF k's are known, so then therefore, by this we can simply calculate delta P I j is equal to GOSF I j k into delta P k, right, that we can simply calculate. So, just this multiplied by this is already known, this we have just now calculated as we have shown. So, then therefore, this is immediately known. So, then therefore, what would be the new power flow over? So, the new power flow over the line that is P I j new, that would be is equal to P I j old plus delta P I j. Now, this P I j old is already known, correct. So, this particular P I j old is already known, this is nothing but the pre-contingency steady state value. So, this is already known, we have just now calculated this quantity from here. So, we will simply add these two quantities and we will get the estimate of that what would be the new power flow over the line. So, then therefore, here what we are doing, so we are simply not using the normal AC load flow, we are simply utilizing some sensitivity factors, or rather this particular sensitivity factor GOSF I j k. Obviously, the question comes into mind that how to calculate them, we will discuss it in some later stage in this course. Now, here what happens is the following. When I say now for any generator, now suppose I have got, let us say, m generators in a system, m generators in the system, let We know that one has to be slack and the rest m minus 1 would be the, let us say, PV bus or rather the generator bus, that we know. Now, the point is, if I say that one generator has gone out of order, so then therefore, this particular generator is not really giving any power. So, then therefore, there will be total deficit between generation and the load. So, then therefore, with all probability this particular system will go into insecure zone of operation anyway if we do not compensate for this loss of generator. For example, if in this system, for example, if in this system, let us say this load is 85 megawatt and let us say this load is let us say 65 megawatt, sorry 60 megawatt. So, then total load is total load. So, then total load is 145 and total generation is 150. So, 150 is equal to, let us say, 5 plus 145. Here we are just assuming that let us say this 5 is loss, just as an example. Now, suppose if this generator goes out, so then therefore, it is not giving 50 megawatt. So, then therefore, in this case what will happen? I have got total load is still 145, but by now my generation is only 100 megawatts. So, then obviously, this generator won't be able to supply all the loads. So, as a result, voltage will automatically come down. So, whatever we do, we will just not be able to operate the system in the secure zone. It will simply shut down after some time, because the amount of generation is not equal to the load. So, then therefore, in that case what we have to do essentially, if we have to prevent the complete shutdown of the system, we have to essentially restore to load shedding, which we do not want to do. Obviously, I mean, restoring to load shedding should be our least priority. So, then therefore, whenever we are saying that some generator is being out, so therefore, we must also say that, well, there is some mechanism to compensate for this loss of generation. Now, in this case what we do? So, when we are talking about this one, so in this expression it is assumed that the loss generation is totally taken by the slack bus. That is the assumption, that is, we assume that this loss generation is totally taken by the slack bus. So, here the assumption is, let us assumption, so assumption here the assumption is that lost generation is taken by the slack bus. We take this assumption because we say that our slack bus is the highest rated bus, or rather basically our slack generator is essentially the highest rating generator. So, then it should be able to take the extra amount of generation, but then obviously our slack generator is not a generator which has got infinite capacity. So, if it does not have infinite capacity, then it may happen that in case of outage of a big generator, then and if our slack generator has to take the or rather has to compensate for the loss of that entire generation by that particular big generator, it may happen that this particular slack generator would be completely out of its rating. So, this assumption, although it is a very convenient assumption, but this assumption is not really very feasible, because there is a chance that in this process this particular slack generation would not be able to supply the entire power, because of the simple fact that it may simply exceed that this particular requirement of supplying the total real power now may exceed its rating. So, if that happens, so then obviously this particular slack generator will also not be able to supply the entire generation. So, then in that case also we have to restore to load shedding. So, to prevent that, what we actually do is, essentially what is being done is that this lost generation, the lost generation is distributed, lost generation is compensated by the other remaining generators combinedly. So, what does it mean? Suppose for example, in my system, let us say there are 5 generators, and let us say, and these 5 generators are 1, 2, 3, 4, 5, and this generator is gone, and let us say this generator has been supplying 100 megawatt earlier. So, then therefore, this 100 megawatt this 100 megawatt loss generation would now have to be compensated by all these 4 remaining generators. Now, the question is how this 100 megawatt would be distributed among these 4 remaining generators. One simple solution is that simply divide them equally, but then that is also not a very feasible thing, because if out of this, if anyone is very small generator, so even taking care of extra 25 megawatt may also turn out to be quite problematic for that small generator. So, what we do is we simply distribute this loss generation to be taken up by these remaining generators in proportion to their MVA rating. So, what we define is, we define some quantity called gamma K, gamma L, which is given by, actually what we do is that we do simply distribute them according to their, according to the amount of real power which they have been generating. So, then what we do is that, or rather we also sometimes do it through their MVA. So, then here what we can do is that S L divided by sum total of S I is equal to 1 to M not equal to L, right. Sorry, not equal to, not, it is not equal to L, sorry, it would be. So, then therefore, what is mean by this? So, I have got 5 generators, 1, 2, 3, 4, 5, generator 3 has gone out. So, then therefore, my K is 3. So, my K is 3, K is nothing but the generator which is experiencing outage. So, K is 3. So, then we calculate gamma 1 as S1, where S1 divided by S1 plus S2 plus S4 plus S5. So, it is nothing but S1 by sum total of Si, I is equal to 1 to 5 not equal to 3, right. So, here in this case, for example, M is equal to 5. So, then similarly we also calculate gamma 2, gamma 3, not gamma 3, gamma 4 and gamma 5. So, for this we would be calculating gamma 1, gamma 2, gamma 4 and gamma 5. So, once we get this gamma 1, gamma 2, gamma 4 and gamma 5, so then now because all these quantities are known, these are nothing but the MVA ratings. Now, because all these quantities are known, so that therefore, these quantities are all constant, they are all constant. So, gamma 1, gamma 2, so these are constant quantities, these are constant. So, then therefore, if these are constant and now the change is actually delta Pk, right. So, if this change is delta Pk, so then therefore, what would be the share of this delta Pk for bus 1? It would be, this share would be nothing but gamma 1 into delta Pk. For bus 2, it would be gamma 2 into delta pk, bus 4 it would be gamma 4 into delta pk, and for bus 5 it would be gamma 5 into delta pk, right. So, then what happens now? So, earlier what we have done, earlier we have only considered that there is a change in the injected power only at bus k, that is at the bus at which this generator is going out of operation. But now because of this, the injected power at all the other buses are also changing. So, then therefore, when we would be calculating the new power flow over the lines, we also have to take into account the change in the injected power at bus 1, bus 2, bus 4 and bus 5. So, then therefore, in this case, so then what? So, then therefore, new power flow over the line, therefore, new power flow over the line between bus I and bus j would be Pij new, that would be equal to Pij old plus delta Pk into, now here just for the sake of just for the sake of convenient notation, let GOSF Ij be denoted as alpha Ij k, suppose alpha Ij comma k. So, change in Ij due to k. So, it would be into alpha Ij k minus, now why it would be minus? We will explain that why it is minus summation, let us say sum L is equal to 1 to m not equal to k alpha Ij L into gamma L into delta Pk. It is quite, so this is the case. It is looking to be quite intimating, but it is not. First thing first, up to this point we have already explained. Why this minus? This minus would be for the simple reason, when bus k is going out of order, then that reactive then that real power would have to be compensated by them. Now, we have already seen that delta Pk, for example, in our case would be let us say minus 0.5, right, per unit, or let us say minus 50 per unit. Just in our example, suppose gamma 1 is let us say 0.1, gamma 2 is let us say 0.3, gamma 4 is let us say 0.3 and gamma 5 is let us say 0.2, suppose. So, then therefore, what would be delta P1? It would be 0.1 into 50 is equal to 5, and we are taking here 0.1 into 50 because it has to now inject more. It has to inject more, because in this case, if I have got 5 generators, for example, if I have got 5 generators and out of this 5 generators, generator 3 is going out of order. So, then to compensate for that, bus 1 or rather the basically the generator at bus 1, we have to now inject extra amount of power, right. So, then it would be injecting extra amount of power, and that extra amount of power would be injected more. So, then therefore, it would be positive. So, then therefore, here in this case it was going actually out of order and it is actually giving more. So, in this case it was actually going, so in this case, so then therefore, it is actually going out of order, and in this case it is giving more. So, then therefore, this would be opposite in sign. For example, here also if we just similarly delta P 2 also would be, let us say, 0.2 into 50 is equal to 10, and let us say so on and so forth, right. So, then therefore, if we apply this, so if we apply this, right. So, by this we would be able to calculate this new power flow over the line between bus I j for the outage of the generator at bus k. For this we need to know this quantity, for this we need to know this quantity, and for this we need to know this quantity. This quantity we have already seen that this is constant quantity. We will be looking into these quantities at some later stage, and we will also see that these quantities are also constant quantity. So, then therefore, because all these quantities are constant quantity, so then therefore, in this case, if there is an outage of any generator, we really do not have to do any kind of AC power flow, we have to simply do some simplest possible algebraic operation, multiply and add. Now, before closing this discussion, here suppose for example, if we just substitute the value of delta p k here for example. So, if we substitute the value of delta p k here, so what we will get, p I j new would be p I j old, delta p k we have already seen that it is actually the negative of the earlier generation. So, it is basically minus p k into alpha I j k, right, and this is here minus and this is also here minus. So, then therefore, this would be plus, because I have got here one minus, and basically this, I mean, delta p k is equal to minus p k. We have already seen in the just a little earlier that delta p k is actually 0 minus p k, that is equal to minus p k. So, then therefore, this minus and this minus plus L is equal to 1 not equal to k up to m delta alpha I j L gamma L p k. So, then therefore, by this expression, if I know what is the amount of generation of the generator which is going out of order, right, and if we know all the sensitivity values, this and this, it is extremely easy to calculate the new power flow over a line without resorting to the complete AC load flow. So, we stop here today. In the next lecture, we would be continuing this particular topic. Thank you.